We want to be able to generate a general Chordic algorithm that will cover circular, linear, hyperbolic in both vectoring and rotation modes. Now we have the Chordic algorithm for the circular values here, the linear here, and the hyperbolic. We want to find the commonalities between these and try to generate just one set of equations. Now the first thing we can note here is that we can jump from circular to linear to hyperbolic by changing just this factor here. So you can see in the circular mode we're going to have this value here, which is a negative. In the linear mode we're going to have this value here, which is just a value of 0. And in this value hyperbolic we're going to have the same as we have here, but it's a positive and it's got the factor of j. So what we can do in order to go from circular to linear to hyperbolic is we could add in an extra term here. Now we could call that term a value of m. Now when m is equal to 1, then we just have this here, which will be circular. If m was a value of 0, then we would have the linear mode, and if m was a value of -1, then we would have the -1 times the minus, which would give us a value of plus. This would give us our hyperbolic. So we can jump between circular, linear and hyperbolic by introducing a factor of m into this term here. Now don't worry too much about this, we'll see it in the next page whenever we write down the final algorithm. Now another thing to note here is that we have different values for our functions. We have our function here for circular, which is arctan 2 to the minus I. We have our linear term, which is 2 to the minus I, and we have a hyperbolic, which is arctan 2 to the minus j. So what we could do is we could just call this one function, and we could just call the function, say for example alpha I, and then we choose each of these alpha i's dependent on whether we're using circular, linear or hyperbolic. So let's go ahead and we'll jump on to the next page and we'll see this written down as one set of equations. So here is our final Chordic algorithm. It's going to cover circular, linear, hyperbolic in both rotation and vectoring modes. The value of x to the I plus 1 is x to the I minus this new factor which we called m times y to the I d to the I, and we have this new factor which is the function which we'll just call alpha I. So we've simply added the factor of m in here and the factor alpha I, and we've done the same. We've done the alpha I in here and we have the alpha I in here. So these three lines here are the basic general Chordic algorithm. Now in order to go to circular mode, we set the value of m is equal to 1. To go to linear mode, m is equal to 0, and to go to hyperbolic mode, m is equal to -1. Now when we're in the circular mode, the value for our alpha I is arctan 2 to the minus I, and linear alpha I is 2 to the minus I, and hyperbolic we have alpha j, which is equal to arctan 2 to the minus j, and we noted that the value of j is equal to I plus 1. Now also in the circular mode we start off with I is equal to 0, 1, 2 all the way up to n. We have our scaling factor here, which is an, which is 1 upon kn, which is approximately equal to 0.60725. And in the linear mode, we have our an scaling factor is 1 upon kn, and that is fixed at the value of 1. And again, I runs from 0 all the way up to n. Now in a hyperbolic mode, we have the value of j starting at 1, and J runs 1, 2, 3, and then we have a repetition at the 4th term here. Then it runs up 5, and it runs all the way up to 13. Now, we've only done the simulations up to 9, so we haven't seen any of these other repetitions, but we would have to repeat it at 13 if we were wanting it to work properly with a greater number of simulations than the number 9. So the next repetition will be given at a value 3k plus 1. So in this case here, the value k starts off at 1, and we have 3 times 1 plus 1, so the first repetition is 4. And then we put the value of 4 in for k, and this is going to give us 4 times 3 is 12 plus 1 is 13 is the next repetition. And the next repetition after that would be 3 times 13, which is 39, plus 1, which is a value of 40. But this doesn't really concern us at all, because we're only going to work up to 9 iterations of our Chordic algorithm, so we just need to repeat it 4. And again, the value for an is 1 upon kn is going to be approximately equal to 0.82816. Now finally, the value for our di can be given by this here in rotation mode and in vectoring mode. So for example, in vectoring mode, the value for di is going to be minus the sign of yi. And we can see that because what we wanted to do is reduce the value for yi to a value of 0 using vectoring mode. So whenever yi became less than 0, then we had to add on an angle. Whenever the yi was greater than 0, we had to then subtract off an angle. So the value for our di would have to be the negative of whatever the value of yi is. So this is our general Chordic algorithm that we can use in order to generate all of the functions that we've seen so far in this course.